Hello and welcome to the segment 2. In this segment, we will build the neural networks using PyTorch. So the basics have been covered. You have seen how to deal with the tensors, how to reshape, how to shape, how to move between different sizes of tensors and also different data types, right? And also we have seen the AutoGrad, which is the automatic machine for gradient computation in PyTorch. In today's segment, we will build neural networks, and in upcoming sessions, we will see how to train and optimize the performances. So in today's session, we will look at the nn.Module, which is the fundamental building block from PyTorch framework. This provides the complete tensor operations which are required to build any neural network you see today. So we will define custom neural networks by subclassing this nn.Module, and also will implement using these different constructors and methods like forward methods. We will use the built-in layers. So as you know that neural networks are built on different types of layers based on what type of neural network that you are trying to deploy or implement. And here we will use built-in layers, and also we'll see how to inspect model parameters, modules, named modules, and compute the total parameter count, which is required to know the size of your model in the end. Again, since we are looking at the training point of view, or let's say we are building these neural networks from training perspective, the same layers will be also used in inference or evaluation. So what is required for that, that also we will see. So how to go from the training modules to the evaluation or the testing. And we will also see how to save the model and weight loading and different checkpointings and so on and so forth. So here we are using tensors as the building block of the nn.Module. So essentially we will import the torch as PyTorch framework, and from that torch.nn, the neural network has these packages and all the modules, the class definitions, method definitions, all the built-in layer definitions, everything is inside this package. So we will not use raw tensors because we will use, basically we need to have the manual tracking of weights and then move to GPU and so on and so forth, but nn.Module will actually help to automate all these processes. Like it will help you to track weights, it will help you to track where exactly the data lives and bringing from CPU to GPU RAM and so on and so forth. So here two requirements, the import torch and import torch.nn as nn. So essentially in this entire presentation we will see that we will be using torch framework as import torch, and now in this class definition you see that we are inheriting from the nn.Module, right? So because nn.Module has all these definitions of the layers and so on. So we have to always call these super dot underscore underscore init underscore underscore. So in the handout also you will see similar implementation. So you are actually overloading the constructor here with the definitions or custom definitions. So here we are creating one linear layer, and here we are creating one ReLU activation. So followed by the linear layer that we have created. And here are the definitions or the sizes or the dimensions of the linear layer that we have had. So input 4 neurons and output 3 neurons. And then we have this forward pass, right? So here x equal to self dot linear. So we are calling the linear forward, and then we are returning the self dot ReLU. So these are the two layers that is running. So the output of the ReLU will be returned from this forward pass, right? So a layer equal to my layer. This is the definition of this layer object, and we are creating this out, which is basically the output tensor or output of this entire neural network will be held in this, and we are calling this layer dot forward. So this is where we are kind of defining these neural networks, right? So this is the basic template of defining any neural network. Now, what this nn module provides automatically, as I said that automatically there are many things happening in the backend, right? Like parameter registration. Anything assigned as nn.parameter or nn.module will be tracked, right? So, tracked for your weights, tracked for your gradient computation that you will do, and so on and so forth. So, module.parameters, it will iterate over all learnable weights. Learnable weights means we have the set of weights for which we want to learn the values for which it will give the minimum loss. So, that is the target, and here we have the model.parameters which will iterate over all the learnable weights or parameters across all the submodules. And model.to will actually see the device where we want to recursively move all the parameters and buffers to the device. Similarly, model.train, model.eval will set the training mode. So, it will have different effects on dropout and batch normalization. So, those things also we will see, because in the training we will take into account of all these layers of dropout, batch normalization, this type of layers, but in the evaluation we will try to evade them, because these are not the neural network base layer, right? And then we have this state dict method which will be used to have the ordered dictionary for all the parameter tensors for saving and loading. So, all these will be automatically done, and nn.parameter essentially is tensor that will have these learnable weights, right? And register buffer will have this tensor that is not a weight but is saved within the model. So, register buffer will have the tensor, but it will not be the weights that we want to have as learnable weights. And then we have this buffer to move. So, .to method will be used for the moving from one device to another device, and basically these are the calls that are required for forward pass, right? Okay, so now if we look at the different types of neural networks, so I have linear layers, it's fully connected layer. You know, if you have learned the basics of neural networks, you know what are the fully connected layer, what are the convolutional layer. Obviously, you have different types of convolution, and layers like normalization layers, then different types of activations are there. You have different regularization is there to improve the performance, like dropout, embedding, multi-threading of multi-head attention, and transformer encoder. So, different types of regularization and sequence layers are also there. So, you can see that here we have tried to accommodate most of the useful built-in layers in different types of neural networks. Like here you have the linear layers, and in the linear layers we can define one linear layer by nn.linear, and lazy linear is also there, which infers in features on first forward call, and these are usually for prototyping, and we widely use this linear, which is fully connected layer, which computes wx plus b. B is the bias vector and w is the weight vector or matrix, and x is the input vector. So, this is your fully connected layer computation, and weights initialized with timing uniform or by default, and we can have different weight initialization also, which can impact the performance as well as the neural network training improvements that we will get. So, basically there are different types of weight initialization. So, there are lots of research is there which is basically to how to start the weights, because if you start weights some particular manner, you will reach to the convergence early. Now, you have the convolutional layers. So, convolutional layers, you have convolution 2D, convolution 1D, convolution transpose 2D. So, different types of convolution layers are there, you know, transposed convolution which is used for upsampling. So, architectures like UNet or this type of where you have these skip connections, you have this convolution and transpose 2D, you have convolution 1D, convolution 2D, and you will be experimenting with the different types of arguments they can have. Like here you have the convolution 2D, here you have the input channel output channel. All these are different numbers which is defining the layer dimensions. Kernel size, which is the filter size, stride, then padding, and so on and so forth. So usually we use 2D convolution for images, right? Useful for convolution 1D is useful for the 1D signals like text representations or audio signal or signals like this, where you have sequences. We usually use convolution 1D, and I said where the transposed convolution is used. Now there are different types of normalization layers also. nn.Batch normalization 2D normalizes across the batch, and it has learnable scale and shift. So I will ask you to go through the implementations, but if you know the algorithm, it is easy to use. So layer normalization is also there. You have group normalization, where we have number of groups, number of channels, and basically this is comprising between the batch and the layer normalization. It is widely useful for object detection tasks. Similarly, you have RMS normalization, which is widely used for your models like Llama and Mistral. Okay. There are several activation functions which are nonlinear functions used in your after the linear layers. You have the ReLU, you have GLU, which is basically the Gaussian error linear unit, which is widely used in transformers. ReLU is widely used for vision tasks or vision algorithms, mostly widely used in convolutional neural networks, where we use ReLU for models like AlexNet, VGG, right? So all these ResNet. You have SILU also, which is also called Swiss, and it is widely used for modern LLMs like Llama 2, Phi. Then you have sigmoid, tanh, which are widely used for your in gates and output layers, basically to calculate the probabilities, output probabilities, class probabilities, right? So these are the different activation functions you can use. And obviously there are regularizations or sequence layers. You have dropout layers, which randomly picks to switch off some neurons or connections. So randomly zeros some fraction, let's say 25% or 20% of activations during the training process. Again, these are widely used for your training. Okay, this has no sequence or use in evaluation, because in evaluation you have this entire network alive. Okay, the embedding is also there, which is used for converting integer tokens to dense vectors. So we will talk about embedding when we will see the implementation of the LLMs and natural language models. And also multi-headed attentions are there, which are widely used in transformer models. So it's full multi-headed attention with optional causal masking. So some attention heads we can mask. So all these things also we will discuss when we will build the actual model for the LLMs and so on. There are transformer encoder layer also, which is used for your feed-forward networks, attention layers, and normalizations. So here we are seeing the model composition with nn.Sequential. So there are different ways to define a model or custom architecture or custom model. So if we want to use off-the-shelf, which is basically already used and already trained model, which is from the library, that also we can import and we can use that. But here in this segment, we are looking at how we can build custom networks or custom models from scratch. So here we are defining this model object, which is nn.Sequential type, and here you can see all the layers are there. Okay. So module, all these modules or layers are defined in particular order, and here order is important because input of each is equal to output of the previous. So here output is 256. So here you can see in this figure, input is X, which has the shape of batch, and 784. So that means 784 is the dimension, output dimension for this X. So this is going as input to the linear layer here, where 784 is converted to the output 256 neurons, right? And this is going to the input of the next layer, which is the ReLU activation. So that's why this order in which we are defining these layers, that is important, and we have to match the input and output of the previous and next layers. Here you can see that 256 is the input and 256 also is the output, because we are basically doing this ReLU activation applied on all the elements here in this vector input. And so you have this batch normalization 1D which is applied on the 256, and obviously you can have different batches. And then similarly we have this dropout, which is 30% dropout, and then linear layer is applied on this input of 256 and output is 10. So basically my output has 10 neurons or 10 such values that you will get from this entire network, and basically this is your model, which is custom model starting from input X with 784 and batch size of batch. We are getting output of batch size of batch and 10 output neuron. So this is your custom architecture. Okay. Sometimes we use also nn.Module, as I have said before, and here we are defining this nn.Sequential. So this is the custom architecture with skip connection. So nn.Sequential we have used to define the layers, sequential layers, which is one after another, and that part you are seeing here on the right side. So layer normalization, and then you have this linear layer, then you have the activation function, and then you have another linear layer with D output. But here we want to have a residual connection. So if you have familiarized yourself with the ResNet type of architecture, you will know what is residual connection is. Residual connection is what? Like here you are seeing that input X is directly also going to the input of this output, where this is concatenated or appended with the or added with the output of the linear layer here and going to the output. So X is applied here in this normalization layer, layer normalization, as well as X is applied here in the output layer or output of the linear layer, last linear layer. So that's why we have this definition of this forward, which is basically taking this entire network, but return X plus self.net X. So that means X plus self.net X is basically output of this linear. So this is how we are making this linear output plus the residual connection. So here we have the residual connection which is going to the output, right? So this forward will return the output, which is basically input of this X running through these layers plus the residual connection. Now we can define models also with like we have sequential. Here we can have the .Module list as well. Okay. So this is another way, interesting way of defining a model. So here let's say we want same layer repetitive. So nn.Linear, which is having D input and D output for let's say 6 time repetitive connection. So module list will actually give you the list of modules that you want to connect with. Okay. But this has nothing to do with the Python list. So Python list is not trackable. Again, that is the similar as using the nn.parameters or nn.Module instead of your raw tensor, right? So similarly here we are not using the Python list, rather we are using module list, where this means that these are essentially the module of the neural network, where we will track the parameters, we will see the weights and so on and so forth. So module list stores many layers and basically PyTorch will track them, and it is useful for loops and dynamic architectures, because if I have changed the range to 5, the number of layer will change, right? So different ways to define this dynamic nature of these layers. This is one way to do that. And here we are seeing that automatically we can define the execution order like sequential. Here layer 0 will be executed before layer 1, layer 1 will be executed before layer 2. So this is the sequence that we have, but we have automated the production of these layers as well as configurable. We are not fixing basically the orientation. And module we write forward because we need to have these residual connection, branching, merging, all these things we can actually use in this module. And sequential was automatic straight line way of execution, and it is easiest for the simpler networks, but it cannot do skipping, branching or merging. So that's why we use module or module list for our definitions. So here you are saying how to inspect the models. So here we are saying that we have defined a model object, which is model equal to my model, and inside your model we have the total equal to parameters. Let's say how many number of parameters are there. So for parameters count, we are running one loop inside my parameter, and we are seeing that how many trainable parameters are there. So basically model parameters, we can see how many total parameters are there, how many total number of trainable parameters are there, and this is one way to inspect the model specifics. We can also see the parameter shapes, because what parameter or which layer parameter has what shape, that also if I want to inspect, we can inspect this. And module tree, if we want to print, we can just print the model which will print this entire module tree. So in the handout also you will see how to run this. Here we are just explaining what are the different characteristics of the model inspecting behavior. Similarly, we can save and load the model weights. Torch.save will automatically save this model as state dictionary in this model path given, and we usually use this method to save weights only. Okay, and we can load weights also. So we can just define another model where we are loading these model dictionaries or the parameters from this path, and it will automatically load the parameters into this model, which will basically initialize all the weights with the weights that have been already saved here. Okay. We can define a complete model, and what example is given here. So this is a complete 3-layer multi-layer perceptron that you are seeing used for classifier. So output dimension is how many classes that I am trying to classify for. Okay. So here you can see that model equal to MLP classifier, which is this object that I am calling for this class that I am creating this object for, and this is taking this into this constructor, the dimension, the input dimension, hidden dimension, output dimension and dropout. So you can see we are giving this input, output dimension and also the hidden dimension and output dimension. So output dimension is 10, means our multi-layer perceptron has 10 classes to classify, and input is 784 and hidden dimension is 512, and we are transforming or transferring this model to the GPU. So dot 2 is basically the device, and we can print the model. It will show the full architecture like this, and basically how many total number of parameters there you can just calculate for each layer. Okay, like here you have input dimension and hidden dimension to the dropout layer. So these are basically the regularization layers, and you have the another linear layer, another activation, and then you have the last linear layer which is giving you the output dimension, and we are basically returning the output dimension as 10 value. Here is one mini transformer for text classification example. Here we are defining this transformer encoder layer, where we are defining this model and number of heads that is there, and feed forward how many depths or dimensions are there. Batch first, normalization first is true, and then we are defining how many layers. So this will actually create the layers. As you can see, we are repetitively creating this encoder layer, and that's why we are using module list. Okay. Weight initialization, as I have said, when we define or initialize one module, as you can see that here we are defining this model object as the model MLP classifier with these dimensions. All these weights like 800k parameters will be initialized with some random values, but how they will follow, there are several algorithms as I have mentioned. By default it will use this method, and it is good for linear and convolution layers, and you can have this custom initialization also. And here is, let's say, Javier uniform way or algorithm that we are using to initialize, that also we can do. And all these biases are initialized with zeros. So this is one instantiation method for your weights and biases in the model. And you can use this model.apply with init weights. It will automatically initialize with all the weights with your custom initialization function or algorithm. So in this segment, what we learned how to build your neural network module using nn.Module, using nn.Module list, using nn.Sequential, and what are the differences. We have seen different built-in layers for linear, convolution, then transformer encoder, and how to inspect model parameters, how to save the model weights, and also how to initialize the weights. So in the upcoming session, we will see how to train the model. So with this, we'll end this session. Thank you.